Hi good people, welcome back. In this video we're going to do some real life examples of factoring and how it can actually be used to solve problems in physics. So we do a lot of these factoring problems, but we don't often get into how it can actually be used. This will be a good video so you can see the actual real life applications of it. I don't know if you recognize this problem, but we did this constructor response way back in December. I think it was on December 3rd. So we actually solved this problem entirely by using the calculator without any real factoring or solving systems. We found a pattern in these numbers in the table. Looks like the projectile started out at 0 feet, then a second later it was at 144 feet, then 256 feet, 336, 384. We looked for a pattern in there by exploring it with constant differences. From that pattern, we were able to deduce the remaining missing numbers, and then we were able to type in this information into our calculator and use the calculator's quadratic regression feature to get this equation here. This was sort of cheating because we didn't really know what quadratic equations were yet, so I'd like to actually revisit this problem and this time do it by hand. We're going to use some knowledge in physics. Here is the physics of a vertically launched projectile. This formula here tells you the height of an object that's thrown vertically in the air, or it could be a rocket that's launched in the air vertically. H of t, that beginning part, is the height of the object at any time, t. T is measured in seconds in this formula. The t that you find here and here is the exact time that you're measuring the height of the object. So the time in seconds since the object was launched. That little lowercase g here stands for the acceleration due to gravity. This could be measured in meters per second squared. It's 9.8 meters per second squared. But in feet, like we have in our problem, that's 32 feet per second squared. You can look that up on Google. It's just a constant, and that's a different constant depending upon what planet you're on, or if you're on the moon, it's a lesser constant. The v sub 0 just stands for the initial speed at which the object was launched, the initial velocity that the object's traveling when it first gets launched. And finally, that h sub 0 is the initial height of the object. And if you wanted to kind of work in terms of our problem, we're on Earth, so our gravitational constant is 32 feet per second squared. If you multiply that 32 by negative 1/2, as you see right here, it's getting multiplied by negative 1/2, multiplied by negative 0.5 or negative 1/2, you get negative 16. So we know that our leading coefficient of our quadratic equation is negative 16. That's the 32 times the negative 1/2. So we do have this part of our equation. And this is always going to be t squared. We don't know the initial speed at which our object's launched, and we don't know the initial height. But we do know that our equation is going to behave sort of like this. So I'm going to go back to my previous page here and see if we can figure out these missing components to get our equation by hand. We're going to use systems of equations to do that. And then we're going to use some factoring to figure out the two questions down here that say find the maximum height of the projectile and also find the height of the projectile, or the approximate times when the projectile will be at 300 feet. We're going to use factoring to determine that. This is a pretty involved problem. I'm going to start out again by writing out that little equation there. H of t is equal to negative 16 t squared plus something times t plus something. And these two boxes, if you want, just for simplicity, let's just call them, these missing things, A and B. A stands for the initial velocity, and B stands for the initial height. We need to solve for A and B. Now luckily we have access to this table up here with some nice known values of t and h, and we're going to make use of that. We know that at 1 second, the height of our projectile is 144 feet. So I'm going to go ahead and replace the height with 144. Replace t with 1. And then we're going to solve algebraically for a and b. But since there's two unknowns, a and b, we're actually going to need to come up with another equation as well. We know that at 2 seconds, for instance, the height of the projectile is 256 feet. So we can use that information. At 2 seconds, I'm going to plug in 2 here, the height of the projectile is 256 feet. I'm going to clean up these equations a little and write them over here. So 1 squared is 1 times negative 16 is still negative 16. A times 1 is just A. B is just being added. And this is equal to 144. Our other equation, 2 times itself, 2 squared is 4, multiplied by negative 16 is negative 64. So we have 256 is equal to negative 64 plus A times 2, which is 2A, plus B. Alright, let's clean this up a little bit further. We can take that 144 and add 16 to it, and we're going to get 170, right? Or 160, I'm sorry. So we have A plus B is equal to 160. And over here we have that negative 64 that we could add on both sides. 256 plus 64 is equal to 320. So we have 2A plus B is equal to 320. This is a system of equations that can be solved by using whatever your favorite method is. I like to use elimination here because our b's have the same coefficient. They're both a 1. If we subtract these two equations, I can cancel out that b. So I'm going to go ahead and subtract here. A minus 2a is negative 1a. B minus b cancels. And 160 take away 320. Oops. 320 is negative 160. So we get that A is equal to positive 160 by dividing both sides by negative 1. And then we had that previous equation, A plus B is equal to 160. So if I plug this 160 up here, I can, over here, I can determine that B must be equal to 0 because A plus B is equal to 160. If I replace A with 160, I get this, and I subtract 160 from both sides, I get 0. So now we know A is 160, and B is 0. This is 160. So we have our equation. Our equation is the height of the object according to the time after it was launched is equal to negative 16 t squared plus 160t plus 0. I'm not even going to write that plus 0 at the end because it doesn't affect it. This is our equation for the height of the object at any time t. I'm going to just go ahead and plug this equation into this calculator here, just so you can get an idea of how the height of the object looks as it was after it was launched. So it's negative 16x or t squared plus 160x or t. Alright, so we can see here that the maximum height of the projectile is 400 feet, and there is another way we can determine that without a graphing calculator. We're going to do that. So let's keep on going with this equation. Write the equation that relates the height of the projectile y to the number of seconds x after it was launched. Here they want us to use x and y, so I'm just going to go ahead and rewrite that using x and y. Okay. What is the height of the projectile after 4.5 seconds? Well, we can just go into our calculator and replace x with 4.5. Oops, 4.5. 648 feet? That isn't right. What did I do wrong? Oh, I forgot to square my x component. So I'm just going to put a little squared up there. Insert, squared, that's better. At 4.5 seconds, it's 396 feet. So we figured that out by replacing x with 4.5. 396 feet. Give the approximate times that the projectile will be at 300 feet. You can see from this graph that there's actually 2 times when this thing's at 300 feet. Here's 300 feet right here. You could see that here it's at 300 feet and also over here. To determine them without the graphing calculator, we can use factoring. I'm just going to go up to this equation here, and instead of focusing on y feet, we have to focus on 300 feet. So I'm going to replace that y with a 300. Oops. So 300 feet, and this is where the factoring comes into play. We're going to use factoring by grouping to determine the 2 times at which this projectile will be 300 feet. I'm going to get the quadratic equation to look how it usually does by moving this 300 onto the other side. And we get 0 is equal to negative 16x squared plus 160x minus 300. Now, this should look to you familiar. It looks like the factoring problems that we've been doing. This is a quadratic trinomial. It has a leading coefficient other than 1, so we're going to want to use the grouping method here, and the first step in the grouping method is to take that leading coefficient and the constant at the end and multiply them together. So the product of these 2 numbers is 4,800. And the sum that we're looking for is that middle coefficient, the coefficient of the middle term there, 160. So we're looking for 2 numbers that have a product of 4,800 and a sum of 160. Now, luckily for us, we don't have to divide 4,800 by every single number up to 4,800. We only have to check up to 69 because the square root of 4,800 is 69.3. So I'm going to begin by just factoring up 4,800 using the brute force method of dividing it by every single number starting at 1. It took a little bit of work, but I found my factor pair that multiplies to 4,800 and adds up to 160. And that would be 40 multiplied by 120. So we're going to use that to expand this middle 160x as 40x plus 120x. Let me rewrite this whole quadratic here. 0 is equal to negative 16 x squared plus 40x plus 120x minus 300. So this is a typical factor by grouping situation. We're going to group up the first 2 terms and the second 2 terms and factor out the greatest common factor from each. So I'm going to use my calculator again. Math over 9, 16, and 40. The GCD is 8. And we can also factor out an x there. I'm going to factor out a negative 8x. I like to factor out a negative whenever it leads with a negative coefficient. Negative 16x squared divided by negative 8x is positive 2x. 40x divided by negative 8x is negative 5. Alright, let's look at our next two terms here, 120 and negative 300. I'm going to use the calculator again, math over 9, 120 and 300. The greatest common divisor is 60. And I'm going to factor out just a 60 because they don't both have an x. 60 goes into 120x, 2x times. 60 goes into negative 300, negative 5 times. Notice that we have this common binomial factor of 2x plus 5. And we're going to pull that out as a common factor. So we have 2x minus 5. When I factor that out of the first part, I'm left with that negative 8x. When I factored it out of the second part, I'm left with that plus 60. And these multiply to equal 0. Now, there's a nice little thing we can use here called the zero product property. When two factors multiply to 0, we know that one or perhaps both of them must be 0. And whenever this happens, we just go ahead and consider each one of those cases independently and solve for x. Because the degree of this polynomial equation was 2, the fundamental theorem of algebra tells us this can have up to as many as 2 real answers, and this one does. I'm going to add 5 here. 2x is equal to 5. Divide by 2, and we get x is equal to 2.5. That's our one answer. Over here, we're going to subtract 60. Negative 8x is equal to negative 60. So we have to do negative 60 divided by negative 8. And we get that x is equal to 7.5. And those are the two answers for when the projectile is at 300 feet. So if we go back to our graph, we can verify that. It happens at 2.5 seconds. You can see that here. It's at 300 feet. And again at 7.5 seconds. It's at 300 feet. So that's because this projectile is launched. It goes up in the air. It reaches its maximum height. And it comes back down and it hits the ground. So it is at 300 feet twice. The shape that this makes, this quadratic equation, is called a parabola. And it is this upside down U-shaped graph here. And parabolas have this nice little property that they're symmetric. And they have this thing called an axis of symmetry, and you can see that this one has an axis of symmetry at x equals 5. The left side of this U is sort of a horizontal reflection about this line, x is equal to 5. Okay, this is the maximum height. There's a nice little property that the axis of symmetry always occurs in between the two zeros of our quadratic. We can see that our two zeros here are at 0 and 10. And if we didn't know that, we could solve for that algebraically, of course. So I'm going to show you how to do that in the next slide here. Our original quadratic that we determined was that the height of the projectile at any time t is equal to negative 16 t squared plus 160 t. If we want to know when this thing hits the ground, we could set the height of the projectile to 0 because the height of the ground is 0. And then we just need to solve algebraically for t. We haven't done much solving quadratics, but again, a good method to use whenever you're solving a quadratic is to factor. So we're going to factor here by factoring out the greatest common factor, which is negative 16t. Negative 16t goes into negative 16t squared t times. Negative 16t goes into 160t, negative 10 times. And we're going to make use of that zero product property again. These two factors multiply to equal 0. So we know that one or perhaps both of them equal 0. Well, we consider each of those cases independently and solve for t. To get rid of this negative 16, we're going to divide. And we get that t is equal to 0. To get rid of this minus 10, we're going to add. And we get that t is equal to 10. So that is the two times when the height of the projectile is 0 feet. And you can see that in the graph here. It's launched at time is equal to 0, so it's at 0 feet in the beginning. And then again, it takes 10 seconds for the projectile to land back down on the ground. Well, what number is halfway in between 0 and 10? Well, to always answer that, sometimes it can be decimals. You just add up the two numbers and divide them by 2. So that means that the axis of symmetry, which is located halfway in between the two zeros, is at 5. So this projectile got launched upward. It came back down. It took 10 seconds for that to happen. And there's this little symmetric axis that we could draw, at which point the projectile reaches its maximum height. That occurs 5 seconds into its launch. So if we wanted to calculate algebraically what the maximum height is, we could just determine the height at 5 seconds. So we're going to plug in 5 for t, and it should line up with our graph that I have minimized here. So we have negative 16 t squared, in this case t is 5, plus 160 t. And that equals 400 feet. So at 5 seconds, the height of this projectile is 400 feet. That is our maximum height. We can confirm that here if you want. This is our max height at 400 feet. You can see that. Alright, I think we pretty much killed this problem. This is how you can use factoring to solve real-life problems. Here's another one that you can try on your own if you'd like. It's a nice try problem. Go ahead and read this. You can pause the video now. I am going to solve it, but go ahead and pause if you want to try it on your own. Olivia kicks a soccer ball straight up in the air at an initial velocity of 31 feet per second. The initial height of the soccer ball is 2 feet. The equation below shows the height of the ball in feet. In terms of time, seconds. This is our equation. We already have our equation for the height of the projectile at any time t. How long will it take for the ball to land on the ground? And what is the maximum height that the ball reaches? So first, to determine how long it takes to hit the ground, we have to understand that the height of the ground is equal to 0 feet. So we're just going to replace our height, h, with 0. And then we're going to factor this. Since the leading coefficient here is not 1, it's a number other than 1, we're going to use the grouping method. So the product of these two numbers is negative 32. And the sum that we're going to look for is this middle coefficient, 31. So we have to figure out two numbers that multiply to negative 32 and add up to positive 31. So 1 goes into 32 times, and you could use both possible arrangements of this. We want this to multiply to negative 32, so one possibility is that the 1 is negative. Another possibility would be that the 1 is positive and the 32 is negative. And 2 goes into 32 16 times. We could use this possible arrangement of the negatives, or this possible arrangement. Both of these will multiply to negative 32. 3 does not go into 32 evenly. 4 goes into 32 8 times. We can use that arrangement or this arrangement. 5 goes into, no, it doesn't go into 32 evenly. Does 6 go into 32? No, we don't even have to check past 5 because the square root of 32 is 5 point something. So we've actually checked all we need to check. So look among these factor pairs. Do any of these add up to positive 31? The first one we tried, luckily. Alright, so we're going to use that factor pair to split up that middle term, 31t, as negative 1t and positive 32t. So I'm just going to rewrite this whole quadratic, negative 16t squared minus 1t plus 32t plus 2. Factor by grouping. Look at the first two terms and the second two terms. Factor out the greatest common divisor from each. The biggest number that divides negative 16t squared and negative 1t evenly, we can factor out a negative 1t. Negative 1t goes into negative 16t squared 16t times. Negative 1t goes into itself one time. Over here, 32t and 2 are each divisible by the number 2. 2 goes into 32t 16t times. 2 goes into itself one time. Notice that we have a common binomial factor of 16t plus 1, and we can factor that out. So this 16t plus 1 comes out as a common factor. When I factor that out, I'm left with that negative t there, and I'm left with that positive 2 there. And this is equal to 0. This is where we understand that these two factors multiply to 0, which means that one or more of them have to be equal to 0. So I'm going to consider those possibilities by equating each of them to 0. That step that I'm doing right now is called applying the zero product property. Now we just have to solve each one of these algebraically. Subtract 1, divide by 16. We get negative 0.0625. So time is negative 0.0625. Over here, subtract 2, and then divide by negative 1. So we get negative 2 divided by negative 1, and we get positive 2 as our answer. Now, this question is, how long will it take for the ball to land on the ground? Which one of these two answers makes more sense? The 0.0625, the negative 0.0625, or the positive 2? Can it take a negative amount of time for the ball to land on the ground? No, it can't. So what we're going to actually have to remember is that this is a mathematical technique that models a real-world situation. So sometimes the math that you're using can result in these type of extraneous solutions. So our two solutions, only one of them really makes sense, the positive 2. That negative 0.0625, I'll plot it like right here, is what we call an extraneous solution. So the soccer ball really takes 2 seconds to land, but it does have that same parabolic shape that we saw in the other problem. And what we also have is the fact that there's an axis of symmetry that occurs halfway in between these two zeros. So somewhere in between these, we know that this will be the max height right here. The max height occurs at a time that's halfway in between these two numbers. So we can actually just take these two numbers, add them up, and then divide that answer by 2. And that means it occurs at 0.96875. So my graph is a little bit off. If I wanted to improve it, I would move this over a little bit, like right there. Can we do this? That's good enough for me. So what is the maximum height that this ball reaches? Well, we know that it occurs at a time of 0.96875 seconds, and that height is, let's find out, negative 16t squared plus 31t, and that t is 0.96875 plus 2. How high did the ball go? 17 feet about. It's 17.015625. And I'm just going to paste that. Because I'm feeling a little lazy. Here we go. That's the max height. Alright, so hopefully this video at least shows you a little bit of how you can use factoring to do some real math where it's something more than just factor this quadratic. This actually shows you how it can be used to solve a physics problem. Hope you enjoyed the video. Please stay tuned for more videos. We're going to kick off our real online learning next week, where we're starting to have some assignments that you need to complete and submit. Please email me questions. You can reach out on Google Classroom or email. Look forward to hearing from you, and I miss all you guys. Thanks for watching.